Let us say you apply a conservative force on a particle and make it move along the x-axis. Then for every x value, you can find the potential energy of the particle and plot it along the y-axis. Then this is what we call the potential energy curve of a particle. So before we go ahead, I would like you to understand one key idea that will make this lesson a lot easier, and that is the relationship between the applied force and the potential energy. Let us start with the easy fact that the work done by a force acting on a particle is force times the displacement. We also learned in the earlier lesson that the change in potential energy is minus of work done by the force. And putting these equations together, we can say delta U is equal to minus F delta X, or F is equal to minus delta U upon delta X. And here these are certain measurable quantities, even if we consider them very small. So the same equation can be rewritten in terms of infinitesimally small values of displacement dx and the change in potential energy du, or F is equal to minus du upon dx. And this equation can be simply read as force at any position x is equal to the negative of the rate of change of potential energy of the particle with respect to position. I mean, it is quite the way you define acceleration as the rate of change of velocity with respect to time. So you see the analogy. Now let us test this equation for its accuracy. So we know that the elastic potential energy of a spring due to the spring force is given as U is equal to half kx squared. Now if you differentiate this equation with respect to x, what you get is du upon dx is equal to kx. And placing this result here, what you get is F is equal to minus kx, which indeed is true and is the Hooke's law. Well, you can also take the equation U is equal to mgx, which is the gravitational potential energy of a particle at height x above the earth, and if you differentiate it, you get du upon dx is equal to mg. And when you place this result here, what you get is F is equal to minus mg, which again is true and a very familiar equation. So you can say that this equation indeed is solid and usable. And with this, you are now set to conquer potential energy curves. So let us consider a particle moving along the x-axis under the influence of a conservative force F that varies with x. Well, the force will do work W on the particle and change its potential energy U as x changes. And if we plot the two, that is the U value and the x value, we get our potential energy graph. Now, if you take the slope of this graph at any point, that is du upon dx, and then take the negative of it, what you'll find is that this value or this expression is nothing but the force acting on the particle at that value of x. In fact, if you can find the value of slope at every point on this graph, you actually get the force value at each point, and you can plot the corresponding force versus displacement graph. So you can see that along this section, the slope is 0, and therefore the force is also 0. And then here you see the slope in this short interval is really sharp, and therefore here you get a high value of force in plus x direction. Then at this point again, the slope is 0, and therefore you get a 0 force here. So now we will understand two important concepts around these energy curves, and they are 1. Turning points, and 2. Equilibrium points. And if you learn these two concepts, you can really master energy curves. So let us first study the idea of turning points. In the earlier lesson, you learned that if only conservative force is acting, the mechanical energy E of a system has a constant value. That is, it neither decreases nor increases and is given as a sum of potential energy and kinetic energy for different x values. So let us rewrite this equation like this. That is, K is equal to E minus U. Now, let us say the mechanical energy E, which has a constant value, is 5 joules. That you can show with a horizontal line like this on the y-axis. In a way, by drawing this line, we are saying that the total energy of the particle cannot exceed 5 joules. Then using this equation, you can easily find the kinetic energy K for any position x of the particle. All you need to do is establish the potential energy U at that point, which is simply the height of the curve at that point, and then put that value in this equation to get the K value. So as an example, at x3, you can see the U value or the potential energy is 3 joules. Then, since the total energy cannot exceed 5 joules, the K value has to be this height, which is nothing but 5 joules minus 3 joules or 2 joules. Then you can see here that beyond point x5, the kinetic energy becomes constant at 1 joule because the potential energy is constant at 4 joules, which kind of fixes the value of kinetic energy. Also, you can see that the value of K is maximum at 5 joules when the particle is at x2 because the potential energy is 0 here. Likewise, it is least at 0 joules when the particle is at position x1. So you see, this is the way you can read an energy graph for K and U values. Next, we make an interesting observation and imagine that the particle has moved into this region. If so, then using this equation, we can say that the kinetic energy value will become K equal to 5 minus 6 or minus 1 joules. But then since kinetic energy has V square in the formula, it can never be negative, which therefore means it is impossible for the particle to get beyond x1 in this direction. So what really happens is that as the particle moves towards x1 from x2, kinetic energy decreases. That means velocity decreases and it slows down till it stops at x1, where the kinetic energy becomes 0. Now, something even more interesting for you. That is, when the particle reaches x1, the force on the particle is positive. And why so, you ask? Well, you see, it is because the slope du upon dx is negative at this point, and therefore this equation makes the force positive. This means the particle does not stay at x1, but instead begins to move to the right because of this force in a direction opposite its earlier motion. So we term this position x1 as a turning point simply because the particle turns in the other direction, and at such points E is equal to U and K becomes 0 and the particle changes direction. Then you can also see at any point to the right of x1, there will be no turning point because K is never 0 on this side. Next, we move on to the second idea, that is equilibrium points. And let us say the mechanical energy E of the particle is now 4 joules. And we can see that the turning point is now somewhere between x1 and x2, which is this. Because here you can see the particle has all potential energy and 0 kinetic energy. Also, you can see that at any point to the right of x5, the entire mechanical energy is in the form of potential energy, or the particle has no kinetic energy, which means no force acts on it or the particle is stationary? Well, such a state of a particle is termed as neutral equilibrium. A simple example could be a marble placed on a flat table where it simply rests even if you move it a little to the left or the right. It'll continue to rest there on the table at its new position. Now, let us say the mechanical energy is 3 joules. Then we have 2 turning points. And why could we make that conclusion? That is, there are 2 turning points. Simply because the kinetic energy at these 2 points is 0. However, you must remember that since the slope at these 2 points is not 0, a force does act on the particle. Here, the slope is negative and therefore the force is positive. And as a result, the particle moves in this direction. While here, the slope is positive and the force therefore is negative. That makes the particle move in this direction. Now, you would have observed that the kinetic energy at point x3 is also 0. However, point x3 is a little different from these 2 points because if the particle is located exactly there, the force on it is 0. Because you can see the slope here is 0 and therefore the particle remains stationary. And if it is displaced even slightly in either direction, a non-zero force pushes it further in the same direction and the particle then continues to move in that direction. That is, let us say you give this guy a small nudge in this direction. Suddenly, the particle will have a non-zero slope. That is, a non-zero force has been introduced that will take it further in that direction. Likewise, if you give it a nudge in this direction, a non-zero force would have taken it in this direction. And we say that a particle at such a position is said to be in unstable equilibrium. Again, a good example would be a marble placed on top of a large ball where as long as it sits there, it will not move. But the slightest displacement in either direction will make it roll in that direction. Now, let us lower the mechanical energy value of the particle to 1 joule. And if we decide to put the particle at x4, it is stuck there. And why so? Simply because it has 0 kinetic energy, that is 0 velocity. That means there is no force acting on it at this point. Now, if we push it slightly left or right, a restoring force will appear that will take it back to x4. As an example, let us say we push it to the right, then you see the slope changes from 0 to a positive slope, and a positive slope means the force is introduced that acts in this direction, which therefore takes it back to x4. And you apply the same logic when the particle is slightly nudged to the left, the particle experiences a positive force in this direction, which again takes it back to position x4. Then we say that a particle at such a position is said to be in stable equilibrium. That is, it comes back to its initial position whenever moved left or right. And if you take a marble placed at the bottom of a bowl, you could say it is in stable equilibrium because it will always move back to this position if you move it left or right. So you could say that if we put the particle in this cup-like potential well centered at x2, it is between 2 turning points and it just about has enough kinetic energy, that is this, to make it swing between this point and this. Well, once again, this is a slightly tricky topic that requires patience to understand and needs to be read in conjunction with a few other lessons. So I suggest that you go through this playlist that will really cement your understanding around this topic of work and energy. And if you like this lesson, please give it a thumbs up and I will see you in the next lesson.